Dobre, without further ado, nech sa páči.
Hey everyone, my name is Sergei Silnov and I'm a Python developer at Espressif. And today we are going to talk about Micropython, which is, does anybody doesn't know what is Micropython? Okay, and does anybody know anything about Espressif? Okay, good. Okay, good. So let's start with Espressif. Espressif is a multinational semiconductor company which is best known for its microchips with Wi-Fi. First success was about 10 years ago when the ESP32 was released, and it became some people use it, but they name it as Arduino with Wi-Fi. Actually, it is a chip produced by Espressif. However, since then many other chips appeared, and not only with Wi-Fi but also Bluetooth, and now with Thread and other tasty things. Also newer chips, like ESP32 it has a special acceleration for matrix and vector operation, which is useful for neural network inference. So today, of course, we'll run some demos. It's boring to listen about hardware and not to see how it will act. Today we'll use a ESP32C3, which is not the most powerful, but powerful enough chip. It has a single-core RISC-V CPU, about 400 kilobytes of memory. This model also has some flash and Bluetooth, Wi-Fi, set of peripherals. All mandatory safety and security stuff is also here. Okay, now let's talk about Micropython. So I have a question to you. Do you know if you have any experience with microcontrollers or something small with, which is usually has only a few dozens of kilobytes of memory, now some few hundred kilobytes or even a few megabytes? Do you know any high-level languages that are popular on microcontrollers?
CircuitPython.
C.
Java.
Java?
C.
Okay. Some interpreted languages, except CircuitPython. Yeah, okay. I found few. Lua and one implementation node MCU. There are also quite a lot of them. I just found one and put it here. JavaScript for microcontrollers. TinyGo, which is a lightweight implementation of Go compiler, and AtomVM to run Erlang or Elixir code on MCUs. However, I asked about popular, and this one never was popular. Yeah, it's unfortunately, higher level dynamic languages not popular on microcontrollers on obvious reasons. Resources are limited and extra level of abstractions are usually eager for resources, so basically no luck. However, Micropython is slightly different thing. It gained a lot of attention, and it can be named as a popular interpreter, a popular language for microcontrollers. First, Micropython, it's not alone. If you ever heard about Micropython, you probably already heard about CircuitPython. What they think, why there are two different Pythons for MCUs. First, Micropython appeared in around 2014. It began as a Kickstarter project. However, it was picked up by community and a lot of contributors started to contribute to it, and it's still in active development. It has quite a lot of nice features. Feature-wise and syntax-wise, it implements almost everything from Python 3.4 and selected features from new releases, like most importantly async and await keywords and some kind of async IO library. And what is also good, it supports almost all Espressif microcontrollers, so you can build your Wi-Fi enabled devices easily in Python. CircuitPython is a fork of Micropython which appeared a little bit later. However, it has slightly different purpose in mind. It was mainly designed as an educational tool for people who just want to touch programming and maybe programming of microcontrollers or to play with some hardware. Often people who use CircuitPython do not have any coding experience at all. What is not always perfect implemented in Micropython, it has slightly different APIs on different chips. It supports many different microcontrollers, not only from Espressif, STMs to name. CircuitPython approach to development is slightly different. You just, if you have a board flashed with CircuitPython, you just connect it over USB to your computer. It appears as a flash drive. You see set of Python files there. Just drag and drop your code there, and it just works magically. It is really nice. However, if something goes wrong, you have to connect it some other way to debug, to actually get access to your output, to your interactive Python shell. It also supports some Espressif chips, but because it initially only supports chips with USB, only ESP32, S2 and S3 are normally supported. Recently they introduced uploading of Python files over Bluetooth, so other Espressif chips should be supported too. Okay. Since Espressif chips are quite popular, there are quite a lot of books about them, also about Micropython on Espressif chips and other devices. And today there are a couple of books that were released just recently, and one of these books I have here today. So think about your questions. This book will be a present for the best question after the talk. Okay, so let's start with important question. Is I forgot to mention. Today we will use Micropython, not CircuitPython. They are pretty close. They have slightly different APIs. Some features implemented better in Micropython, some implemented better in CircuitPython, like USB support, or if you want to make a USB keyboard, you probably should go CircuitPython. If you want to have some better level control, like work with interrupts, probably you should take a look on Micropython. But in general, I would say they are on par these days. And they're definitely good for education and some small hobby projects, but are they good for something serious, like serious? Some time ago, I asked this question. I asked myself this question, and one of the attempts to answer this question was a master thesis done by Indra Shestak here in Brno. He made an implementation of Wi-Fi mesh in pure Micropython using ESP is a proprietary protocol supported by ESP chips for point-to-point connections, and it kind of worked. It wasn't most efficient implementation, it wasn't fastest, it doesn't support a lot of nodes in the network. I think his implementation worked well up to 10 nodes, but with some cleanup in codes and some optimizations it can do much better. Unfortunately, it wasn't just a thesis, he didn't have enough time to do everything. However, there are some brave people who actually use Micropython for commercial products, and even so sensitive as a hardware keychain. And it works. It's a commercially successful product. It's named Trezor. As you can guess, it's a Czech project. And they have pretty big code base. I'm pretty sure some of you are familiar with this project. Does any? Okay. However, recently they started to also, introduce some Rust into their Micropython code base, but it's a different story. Okay, I already mentioned that we are going to experiment today with ESP32 based dev kit. This particular dev kit was released as by our Rust team to make demos in Rust, but it's equally good for Python demos too. It has one multicolor LED, couple of sensors like temperature and humidity, couple of one button, and basically it's more than enough for us to start today. Okay. Let's start, actually. I suppose we'll make today demo slightly interactive, so to start you will need a couple of tools. First, first you need to flash interpreter to your dev kit or you're going to use. For this you can simply download, go to Micropython webpage and download pre-built binary which you then flash with one command. If you want to modify something in Micropython codebase, make some configurations, how much heap it will give to your to a board, you can always compile it before flashing. It's pretty well documented on Micropython's website, so I won't stop on this now. So I already have, it's the same dev kit, just in case, so I already have Micropython flashed on this, so we can start with simple example. It's pretty simple, but let's try to run it. So first I just copied file. I'm using here a separate tool for named Impir Mode. This tool is a part of Micropython project. It allows to copy files to dev kit over a serial interface. Most dev kits, when you connect them over USB, they provide they're seen as USB to serial converter. So you can use this serial interface to upload code and also to monitor what's going on your board. So first we just copied a file using command cp, and now we can just connect and see what's going on. I forgot to, after I copy, it is necessary to restart the microcontroller. Yeah, it looks like it works. Okay, now let's make something a little bit more bright. As I mentioned, this dev kit has one LED. It's not a simple LED, actually it's an addressable LED, and you can it can the color can be configured with a special protocol. The library Micropython supports this protocol because it's pretty common. There are many LEDs, but they share the same protocol. A library built into Micropython named NeoPixel. So what's going on here? Let's go this code line by line. First, we need to create an object of pin which represent one leg going out of microcontroller itself, where this data line of this smart LED is connected. On this board it is connected to pin number 2. Then we just create an object of NeoPixel and pass this pin object to the constructor. Second argument is actually a number of LEDs, because these LEDs can be chained and you often see them in different decorations where they are used to create light animations. Okay, the rest of the code is relatively simple and straightforward. We set some colors in a cycle. Here we just we can access elements of our LED object as a list and set some values. Then we can write a method to actually send data through interface. And after every update, we sleep for 10 milliseconds. Okay. Okay, now I will restart, and it starts changing colors. Cool. I like it. Okay, let's try something else. As I mentioned, this dev kit also has a button. Let's push the button. We'll push a lot of buttons today. How we can handle button presses in Micropython? One, the most obvious way is basically just sit in a while loop, waiting and checking whether button is pressed or unpressed once in a while. And this is pretty simple and it works. Code is pretty simple. Here we create a pin object. Unlike in previous example, instead of output we say it is an input now, and we just check it value. If it's 0, it means when the button is pressed, it connects button to the ground line, so value is low when it's pressed and it is high when it is unpressed. Okay, let's try once again. Next example. Button not pressed. Sorry, wrong button. It was a reset button. Button pressed. Button released. Quite works. Okay. However, if it's not really convenient to have a giant loop, and if we want to do more things than just checking for state of one single button, we of course can add more things we check once in a while into this loop, but it's not really convenient. More common way in embedded world is to use interrupts. So basically what we are doing here, it's pretty the same. We define a function which will be called whenever our button is pressed. So what we'll say here, that for this pin number 9, whenever it level goes from high to low, like voltage goes from signal level to 0, we call back, which basically prints. And it works sorry. This word. So whenever I press button, on every press, it prints. Works just fine.
It looks like it's responding to, being kept down, not to the edge.
I will about it just in a moment. Yes, sometimes it may happen. Okay, this is nice, however it's also not always perfect, because we cannot put a lot of logic into this interruption callback, because nothing else will happen while this handler is running. Luckily there is another way to deal with buttons, and here comes async.io. Async IO, as you probably know, is Python way to implement cooperative concurrency, and it is available in Micropython. So what we'll do here, in this example, at the first look looks quite close to the very first one, where we just waited for the button to be pressed. However, there is a slight difference. First, async and await keywords, and we run this this function which actually checks and does the job using async IO run. If you're familiar with normal Python's async IO, it creates an event loop and then schedules the task in this event loop. The good thing that every time when we await something, it can switch to another task which awaits to be processed and requires some processing time. So it works well, trust me. Or we can try. Okay, let me explain what. No, it's a different thing. So every time I press reset instead of right button, it also disconnects from serial converter. Many dev kits, they have a separate chip as acts as a USB to serial converter. However, this chip is ESP32C3. It has built-in USB to serial, so there is no need to separate chip on the board. However, it has a downside. When we reset the whole chip, this part is also resetted, so USB to serial USB device temporarily disappears from computer, and if we have some process communicating with it, it fails. So I will try to not press wrong button. Yeah, so it works. When it press, button is pressed, it just keep printing. Small off topic. How we can test actually our programs we intended to run on microcontrollers. There is no way to run debugger on microcontroller with Micropython, at least so far. At least I don't know any, as it said. And it still requires some copying of your files. And as for tests, I don't know any Micropython test frameworks either. However, anyone who had ever wrote code compatible both with Python 2 and Python 3 should have no problem to write code which will be compatible with both Micropython and regular Python. Sometimes we need different imports here and there, but in general it's possible to test all business logic which not deals with hardware itself on a desktop Python, have it covered and only focus on embedded code when it's or mock some peripherals in your tests.
So what about emulation?
Yes, it's possible. So maybe
We can we can run it in QEMU for example.
yeah,
Then
and
you
there
would
is also I always refer to you as to say a couple of words about Wokwi.
So shameless plug.
Yeah.
There is wokwi.com, wokwi.com, and
Yeah.
there is tons of Micropython stuff already there. So there is already a simulator for a majority of Espressif chips, so you can run it inside the simulator in the web browser.
Yeah, and also it provides some editor, so you can connect some peripherals like LEDs, buttons, and
So, you know,
What's the address again?
Wokwi.com.
I will share it on a Discord server that I will advertise later.
Can
Okay.
you type it on the console so it's on the
Yeah.
recording?
.com. Yeah.
Yeah, it has even this week there is a new cool feature. If you hit the pause button, it will display.
It's very low.
Yeah, it's
Oh,
there.
okay.
the projector is misaligned.
So
There.
yes,
If you hit the pause button when you run the simulation, it will show you the status of the pins, so you can see what is there on the GPIOs. That's pretty nice. That's edit this
Mhm.
week. So wokwi.com.
Yeah.
Pretty neat. End of shameless plug.
Okay. The problem you asked that sometimes when I press a button, it doesn't look from electrical point of view like single press, like because due to physical reasons, button is just two metal plates that are touching each other, and sometimes they are wobbly. So when you touch, they're bouncing. And from electrical point of view, it looks like a lot of turning on and offs in a short period of time. Then it actually settles down and it feels it's pressed. So to proper handle buttons, we should also add some weight. So basically, to wait a little bit, typically. 10 of milliseconds before this process to settle down. Here is just, it's not really optimal maybe, but it should be working. Like I will scroll up a little bit. The whole full code is a little bit longer, but what happens here? We basically create an object, our button, which is the bounce, which will output which will handle presses correctly, and we can provide it to coroutines that it will run when button is pressed or released. We can also configure whether if button normal state is low or high and the bounce time. I won't stop for too long, but whenever you deal with buttons, it's important to think about the bouncing. Okay, now let's go further to interesting part. This chip is Wi-Fi enabled, and usually you want to use it for having something connected. Everything is better with Wi-Fi. I didn't expect that there will be a good Wi-Fi, so this example is how to connect to existing network, but we won't use it. We'll create our own network. Code is pretty similar in both cases, so I will go through it. We create a wireless LAN object saying that it will be an access point. We set in active and configure a network name, password, and authorization node. Number 3 means WPA2 PSK. And basically that's it. So let me it should create an access point. Yeah, it created an access point. Okay. Give me a second. Okay, it created an access point, and now we can connect. But it just created. Please don't connect everyone. It can handle. Probably it can handle all of us, but I'm not sure. I must set different passwords than person in slides, but okay. Whatever. So now we changed a little bit a way how we call. So we define an async main function and define all the coroutines that we want to run in our main function and just run it. Okay, now let's make something useful with this access point. A good thing is to run a web server. We cannot run Flask or Django on this tiny device, but there is a framework named Microdot, which provides interface quite.
We were trying to guess the password.
This password.
It was on the slide.
There was just a variable. I didn't see the string itself.
Yeah.
Oh, okay. Maybe I didn't show it, so that's good. It will survive for a bit. There is a framework which is pretty similar to Flask and pretty small, so it can run on microcontrollers. With Micropython, it's specifically designed to be used with both big Python and Micropython, and it also async, so which is really nice for our use case. How if you want to use some library with Micropython? Micropython provides a way for this named mpip. It's a built-in library. So basically, whenever you have actually I forgot to show the REPL. I will stop for a minute and we'll make some introduction. So the idea is when you have your board connected to Wi-Fi, to internet, you basically can run in your Python code mpip, install and provide the name of the package you want to download. I don't really like this way because when I develop something, I develop on my big computer and I want to have all files of my project first on my development machine and then copy them to my board. So I usually just add whatever repository with library I want to use as a submodule to my project and have a tiny script or make file just to copy all the files I need to dev board. Luckily we don't need to copy too many files for Microdot. It comes in 2 files. If we want only classic synchronous interface, we need only 1, and async features are in the second one. Okay, so let's write some web service. It will be very powerful. Anyone familiar with Flask should recognize this code. It works roughly the same. And if you run it, it should render a web page with is number 1. Okay, let's try it. Okay, let's give it a second. Yeah, it's created a page. Now let me open my browser. Connect. Connected IP address is 4.1. And it runs on port 5000. Yeah, and as you can see, we have number 1 here. I can make it a little bit bigger. Okay, nice. I'm really happy that all demos work. Now let's glue everything we made so far together and make a big demo. So you see we have this LED changing its light. Whenever I press wrong button, everything breaks. So far, when I press button, nothing happens. But if I'll go to browser and refresh, you see, with every press, number increases. Actually, when I press button, it increase for 0.5, and when I release, to another 0.5. Let's go back to the code. Actually, it's pretty similar to what we already saw, with a couple of adjustments to make all the parts async. We just defined a global variable with this number. By the way, now I made all demos so you can see the password and try to kill this small Wi-Fi device. We create a hotspot. We define this button class. We defined now asynchronous method. So it actually differs with only in 2 lines. Async here and await async IO instead of time here. And then in our main function we initialize button, create task which blinks, connect, wait for Wi-Fi connection, and create a new task that runs the server. Well, it's not really necessary here, but in previous demos I just had this line because when we have something short running, when all the tasks are done and nothing runs in the background, it just stops. But if you want to have it running forever, we probably need to do something, add some coroutines that will run forever. Okay, so now the question how well it works. I already started a little bit in the beginning, but actually performance-wise it's a slower than C. It is much slower, even though Micropython developers, they made an incredible job making it possible to run with just few dozens of kilobytes of memory. Well, you even though you can run interpreter, you cannot do a lot of things if you don't have enough memory. By the way, how much memory do we have? This is not what you commonly do on a desktop Python, but you do it pretty often, and you do care a lot about memory consumption when you work with Micropython. So here we have 86 kilobyte of memory free and 37 kilobytes of memory used. And notice a thing, every time I just run this function, it uses 134 bytes of memory. It's not a big thing, as it may, but when you have only 100 single method call consuming like 100 of bytes, it's too much. And what is more important, garbage collection works entirely differently on Micropython than in CPython. Actually, it's a bitmap garbage collector, and it doesn't run while you don't. It never clears your memory until you run out of it. When memory is full and allocation is failing, it tries garbage collection first and then run it. So if we run gc collect, let's check how much memory we have now. We have 10 kilobytes, keeping in mind that these background things may be running, maybe not.
Hypothetically, could you fill the memory for us? That's something thoroughly. Could you fill the memory for us? Just to see how it handles the.
I guess you can do like while true and then.
Or just
yeah.
just allocate a very large and stupid list or something.
Okay. Even though we likely have enough memory, it's a common problem with embedded Micropython development, memory fragmentation. Because we were growing in memory use, there are some parts of memory.
Just to be at one stretch.
Yeah, it must be one stretch. It cannot allocate. So if we'll try something smaller, it will work. And probably we will be able to run it 10 times without any issues. But not that big. Also, if we go to the code, it's common to actually run gc collect from time to time you use it. It's a common pattern to run it every time you make some imports, because every import creates a lot of allocations which are not needed after it finished. There are also more techniques to optimize both performance and memory consumption. One thing I didn't cover today is to precompile your Python files into bytecode and copy bytecode files to your board. Second thing is just write your code uglier. too many too